Hello, everyone. Welcome to the last episode of our series on exploring Autodesk Inventor. And this episode, we're going to be doing something very interesting that's not part of the norm whatsoever, which is going actually to a small presentation mode where I'm going to talk about von Mises very briefly and finite element analysis. So finite element analysis, or more commonly referred to as FEA, is the way in which we analyze how items are going to experience the two items of stress and strain. And so these two things are very different, and we need to make sure that we understand how they interact and how they're related. So let's talk about a very simple object. Let's say that we have a let's say rectangular prism of aluminum, like this, 6061 aluminum, usually most common in manufacturing, like this. Let's give it dimensions, or let's say it's a foot, so 12 inches, and that it's 2 inches, and then this is 1 inch. Perfect. All right, so now that we've defined this, and the dimensions are really arbitrary, essentially what we want to say is, let's say that this is just bonded to a wall. For the sake of us, let's not do something complicated like it's bolted or whatnot. Let's just say it's welded to a wall. So we can assume that it's merely just an extension of a giant wall that we have right here. All right. Now, how can we determine when it's going to break? And what I mean by that is, if we had some sort of a infinitely thin rod that ran through it, and assuming that it has a far greater yield strength than this aluminum piece, and we had a hook on it, if we attached weight to it, we know that it would eventually break. Eventually, this would experience an insane amount of force, and it would start bending. This is called deformation. And there's a certain point at which it will deform beyond the point of no return, and we will not be able to, unfortunately, go back from that. And so the real question is, how can we determine when that is? And honestly, there are lots of different ways to do it, because there are lots of different theories behind deformation for ductile materials, which are materials that can bend, as opposed to brittle materials, which are things like wood, things like usually some plastics. And so the plastics in themselves get very complicated. So materials that are very brittle as opposed to materials that are very ductile have different theories behind them. And so the most common way to do this is by either carrying out an experiment, of course, or by doing finite element analysis in a simulation. And so finite element analysis is essentially the idea that I can use stress and strain to form a very good estimation of how things look in the real world. And so let's say that I have this rod again, and I were to have it, let's make it very simple. Let's make it 2D this time, and say that I have it sitting on this table. Let's say there's a high coefficient of friction here, so that it's not really going to move on this table. And I have two opposite forces on it. Let's say that I'm exerting these uniformly on these faces. This is obviously not a good example because I'll probably need to grip it, or I would need to bond something to this here. Let's say for the purpose of this experiment that I am just somehow exerting an outward force on each side. Well, stress is the idea that I have these force elements that are exerting these force elements on this piece of material. And so it's very important to be able to understand the effects of stress on certain materials, because the effect of stress is going to determine when and where the limits of these materials is going to be. Obviously, we wouldn't use something like polylactic acid to 3D print something like a bridge, simply because the yield strength is not as durable. It's not as durable as something like aluminum would be, and so that's what we use to build our bridges. So what we can usually see is if we plot stress here, plot strain here, effectively what you'll see is strain is defined as the amount of deformation, usually expressed in many different forms, but in this case, most likely would be an, an area. And so strain is going to tell us how much these items deform under uniaxial tension, which means in one direction. So how much it's going to be deformed in a particular direction. And so what you'll find is, unsurprisingly, especially for material like aluminum, you're going to have to exert a whole lot of stress to get relatively little strain. And so let's say that this is going to be something like 500 to 600 megapascals. And then this is going to be in some sort of cubic measure. And so there are two important points that you see around. So you see, actually, more accurately like this. This point here is going to be, and this will probably go a bit higher. This point here is defined to be the point of the elastic limit. So essentially, for a material that's relatively ductile, this is going to be a lot higher because it's the point at which, if I have something that can bend, so let's say something like, I don't know, a piece of polylactic acid plastic or ABS, then this is going to bend and bend and bend and bend. And if I let go, let's say around here, then there is a most likely this material is going to be able to return to its starting state. So think of it like, it's if you've ever played around with door stoppers, they're usually coils that have rubber on them. If you ever flick one, move one down, it'll obviously bend something like this. But then when you let it go, it'll wiggle a bit, and then it'll go back to its initial starting position in a very, telling elastic fashion. And so that's where we get that from. However, after this point, you've deformed this material so much that it is no longer going to return to its initial configuration. This is permanently deformed. And then this point over here is where you rupture this item. So this is usually going to be when something breaks. So if you have something that's more tensile, most likely something that is brittle is going to just break here. It's not really going to reach an elastic limit. It's going to bend very little, and then it's immediately going to get to the rupture point. All right. So now that we've defined all of this stuff, we're going to talk about how finite element analysis works in a simulation. And essentially, if I have this material, the way I perform stress analysis on it is by breaking it up into finite elements. So if you've ever done any topics within mathematics and calculus, you'll know that in calculus, we have this idea of the integral. And so the integral, and again, if you're in middle school, don't worry about this, I'll explain it. So the integral is this concept in mathematics that, in summary, if you have a function, f of x, or f of really anything, so let's say this is f of, these are stress elements, stress z, and these stress elements are going to just be the stress in each direction, so in the x, y, and z direction. So these stress elements can be put into a function, and then this function is going to output, of course, anything from the the deformation or strain, and going to be able to, and is going to give us the effect of what the force that we exerted of the stress. So if we plug in all of these stresses in here, we're effectively going to be able to observe strain, or the effect of deformation on this object. And we would also be able to calculate something like this, which would be the yield strain. There are many different ways that you can write this out. There are a lot more, this gets a lot more complicated. And so I definitely don't want to explain that too much, simply because it would take a whole lot longer in the video. However, the important part of this function, we'll call it f of dot dot dot, the dot 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 symbolize all the stuff that I put in there. The integral of this function, if it's going to give us the strain, what this integral will do is it breaks it up into components. And so let's say I am walking. If I am walking somewhere, this is me walking, I have a function f of x that is going to help me define my position. So if I'm walking, let's say I'm not accelerating, which means that I'm not going fast or I'm just going at a particular velocity. X of velocity, v naught, which means starting velocity. If I walk and just walking, then this function is going to be able to tell you what my displacement is, which is the distance from where I started at a given point, at a given time. So you'd also need that time. And so what's so important about this? Well, what I can do then is, if I wanted to determine my velocity, then what I would do is simply just take this constant. This constant is simply my velocity, right? My velocity at a given point is always the same thing. So my velocity would be v naught. Why am I telling you all this? Why does it seem so confusing? Well, let's say I have the speed that I'm going at a particular point. And if I know that I'm going this speed all the time, as long as this speed is always there, what I can do is integrate it. And this integral is going to give me a function, vt. Well, what does vt mean? Well, if you guys remember what velocity is equal to distance divided by time. And so if I give you velocity times distance, velocity times time is going to give you the distance I've traveled. In other words, if I integrate my velocity, then it's going to give me where my position. And so very similarly, if I am exerting the same stress all the time, kind of like how I'm exerting the same velocity all the time, this is F for force. If I'm exerting the same force all the time, just like I would exert the same velocity all the time, if I integrate this, it's going to give me the element of position for velocity. And for force, if I integrate this, if I integrate this function that I gave earlier, this dot dot dot, I'm effectively going to be able to get the stress on this, or the deformation on this component. Does that still seem complicated? Yeah, I wouldn't be surprised. But the way integrals work is essentially, if I were to break this up into different parts, let's say just cut this up into different small boxes, and just doing this kind of randomly, but let's say these are all just pieces, like a Lego. These are all individual pieces that make up this giant rod. Then what I can do here is make a pseudo integral. So a pseudo integral can give us the deformation. And so this is going to tell us that, hey, if I were to break this up into an infinite amount of pieces, a sheer immense amount of pieces, then what this is going to do is give us an integral. An integral is saying, if I have this thing, this result, so in this case, the result would be the deformation. this f of t is the deformation of the object, I can get the deformation of the object by breaking something up into infinitely many things. So let's talk, going back to our analogy here, the way you calculate velocity, the way an integral calculates velocity, this thing that you do to it, this integral will just say, all right, well, I have a time. This is my end time. This is my start time. Well, what we're going to do is break up your journey. We break it up into 2 steps. Well, the integral takes it a step further, breaks it up into 4 steps, breaks it up into 16 steps, and it goes on and on and on and on until your journey is broken up into an infinite amount of steps. And so what this says is, all right, now what we're going to do is just take these almost like infinitely small steps and say, all right, let's see how much he moved in this step. Let's see how much he moved in this step, and this step, and this step, and this step. And then it's going to add all of those up. And so if you want to approximate an integral, because obviously you can't cut this up into infinitely many small parts, but you can sure try, you break it up into finite elements, which is a certain amount of items that you break it up into. So see, now this is broken up into, I'd probably say 20 or 30 different components. And that's going to give you more or less a pretty good approximation of how this item will behave under stress. And it will give you the von Mises analysis of all of these elements. These individual things are called elements. What are von Mises? Well, von Mises is essentially going to tell you what areas are experiencing the most amount of strain as a result of this process. It's going to tell you what areas are experiencing the brunt of this stress in layman's terms. So let's see how this is going to work in action, and hopefully it'll make a bit more sense. So I'm going to jump over and share my screen on my computer. As you can see, we have here a wheel, very similar to the one from the previous episodes. And let's say I want to simulate how much it's going to take to crush this wheel. Let's say this wheel is bound to an axis. So let's go to simulation, stress analysis. All right. So we go to constraints. We go to we go to manage and then create study. So this is going to create a simulation. All right, don't worry too much about that. So now what we need to do is say, all right, what are our constraints? Well, you can add a pin, which is going to be some sort of axis that something rotates on. Frictionless constraint, so just something that is bound, and then fixed, something that's going to stay. That's not going to change at all. So this is just hooked in place, more or less. I would normally use a pin because, of course, this is going to be rotating. But let's say that this is bound to the axle. Let's say it can't move. So let's zoom in a bit. There we are. So this is now bound, permanently bound. Great. So now that we've done that, what we're also going to need to do is add in, of course, our load. So pressure is going to be sort of a crushing force. Force is going to be just an external force. So let's say we're going to exert about 8 pounds of force onto this entity. Great. All right, let's exert it onto the outside rim. We're going to hit apply, 8 pounds of force. Great. Now all I need to do is close up. And now we have this force that's being exerted on this wheel. The last thing you want to do is to define the material of the wheel. And all you need to do that is right click on here, go back to modeling, go to the wheel, right click on it, go to eye properties. You could also go to the eye properties up here or in one of the other tabs. And then we can go to the physical. I've already defined this as as ABS plastic, but you can define this as any other material. And you can also define custom materials, but for that you need to calculate the inertial properties of this. And that would take quite some time. So I'm just going to define this as ABS plastic. We're going to close that up. And now we should be good to go. Now all I need to do is show the mesh. So the mesh, I'm going to go to mesh view. This is telling us all of our little elements. And I told you that we're cutting this up into parts using what we call a Riemann sum, which is basically a part, kind of like an integral in a sense. And what we're going to do is cut this up. So now that this is cut up, you see these individual triangles and some such that are defined. And so we're going to see what the individual force elements are for all of these components. Let's say that I don't think that this is good enough, that this isn't going to give me a good estimate. Then all I need to do is go to study, go to mesh, right click on the mesh, and then go to mesh settings. Then what I can do is change this. So maybe I want the average element size to be smaller. Maybe I want it to be 0.05. Of course, minimum element size can't be greater than my average element size. Let's say, as a fraction of average size. Never mind. Yeah, that should be fine. Okay, so let's do that. That should be good. Maximum turn angle essentially means the angles of these triangles. I'm not going to change that at all. And then we're going to be okay. Now it's going to give us this little lightning bolt. That means that it needs to be updated. I'm going to right click, and let's say I want to change just the stuff right here. Well, what I can do is go to local mesh control and click this side right here. And I want there to be, let's say I want the stress on the element size on there to be 0.01. Right? I'm going to change that. Now, what I can do is right click on here, go to update mesh. It's going to take a couple seconds to update, I think. Let's see how long it's going to take. Oh, there we are. There loads mesh. And there we are. As you can see, we have a lot smaller elements here, very, very tiny. And this is going to be a bit more useful to us and give us a very, very accurate estimate of how this item will work. Usually you only need about 30 to 40 individual elements. This is probably close to at least 500 to 700 elements. At least, maybe it's closer to 1,000 or something. But without further ado, let's do what you all came for and hit solve, simulate, and then run the study. And let's see what happens. Maybe. As you can see, it's taking some time because of all the elements that we have. And now it shows the deformation. And this makes more or less a lot of sense because, well, if you exert a force on the outside of this material, chances are at these spokes where it's a whole lot stronger, it's not going to have that much deformation. Meanwhile, here where there's next to no support, of course you're going to have deformation. And so that's a very important part of how this material is constructed. And as you can see, this is going to give us the von Mises stress in the top left corner. And so it's going to number that off from a certain value minimum to a certain value maximum. Generally speaking, different items have different stress tolerances, but the von Mises stress on here is relatively low, about 0.1. So chances are you're not going to see an immense amount of permanent deformation on this material, if any. So thank you so much to everyone who tuned in for this episode. I've really enjoyed making this series. One last thing that I do want to go over is once I finish the analysis here. Oh, there's also a simulation component that I forgot to mention. If I go back here, I can actually animate the result. Oh, no, I can't animate the result. Let's see. Static analysis. Nope. Let's run another study on it real quick. All right. Now I can actually animate the result. That's something really cool I wanted to show. You can see it crinkling up. And so that was the last component I wanted to talk about. One last thing that I wanted to do that's not related to this episode is we've talked about drawings in the past, and I completely forgot to talk about one important part of drawings, which is you can go to, which is the modify tab. In the modify tab, I'm not going to talk about the slice, crop, or breakout sections or break. Break is very important. That if you have something like a very long rod that's more or less the same for a great stretch of distance, it would be cool to just cut this up. So let's say we talk about, let's say that we talk about this section right here is more or less the same to all of this stretch of length. and then that would cut it up and show that distance there. Obviously, that's not the case for the wheel, so I'm going to get rid of that, but that's the last element I wanted to talk about. And so I hope that everyone had a great time with this series and that you continue to succeed in Science Olympiad in the future, as well as any other sort of engineering-based activities that you compete in. Oh, one last thing, also talking about section view. Section view is where you can take a line on a component, right-click, hit continue, and then what you get is a sort of sliced item. So this is going to show you the interior as if this were cut along this axis here. All right, so that is all for drawings. 2 things that I forgot to include in a previous episode. So as I was saying earlier, I hope that you all continue to succeed in Science Olympiad and your engineering endeavors. Best of luck at any Science Olympiad-based competitions that you compete in, as well as in your architectural, civil engineering, mechanical engineering, etc. adventures. All right, thank you so much to everyone, and good luck.